Imagine like harnessing the power of a star, but not like light years away right here in a lab.
It's pretty wild.
That's what we're diving into today. A major breakthrough at SLAC National Accelerator Laboratory.
Yeah, you sent over some really interesting articles about it.
I know, I'm so excited to dig in and see what it all means and why people are so hyped about this.
Yeah, definitely. So basically, researchers at SLAC, they created this super intense submicron electron beam,
Okay.
and it's actually the most intense one ever produced.
Wow.
Yeah, and to give you an idea of just how intense, we're talking about an ultra-short pulse of electrons
Yeah.
that has a peak current 5 times greater than anything they've ever achieved before.
That's a huge jump.
It really is. And it's not just about like cranking up the power. They had to come up with a whole new technique using lasers to achieve this kind of power and control at such a tiny scale.
That's what I find so fascinating about this kind of science. It's not just brute force, it's elegant problem solving.
Right.
And this leap in power and control, it really opens up so many possibilities for scientific discovery.
Oh, absolutely.
Like we're talking about probing the fundamental laws of physics in ways that were basically impossible before.
Right.
From the quantum realm all the way to distant stars, it's pretty mind-blowing.
So to really appreciate what they've done, I think it helps to understand how electron beams are usually created.
Okay.
Traditionally, they use these things called microwave fields. And it's kind of like, imagine you have a group of runners all starting a race at slightly different times.
Okay, like a staggered start.
Exactly. And the microwave field, it acts like a force that pushes the runners who are lagging behind so they all bunch up and move together.
I see, so it compresses the electrons into a more focused beam.
Precisely. But here's the catch. As these electrons accelerate, they start emitting radiation, and that makes them lose a bit of energy.
Oh, so it's like the runners getting tired and slowing down.
Exactly. And this loss of energy, well, it kind of messes with the quality and the focus of the beam.
So you can have a powerful beam, but it becomes really hard to keep it precise, especially at very small scales.
That's the trade-off they've been struggling with.
So it's like this balancing act between power and control, and it sounds like that's a pretty fundamental limitation.
It is, and it's something that's been a major goal in accelerator physics for a long time.
Okay, so how did the scientists at SLAC overcome this hurdle?
Well, they had this really clever idea. They adapted a technique that was actually developed for X-ray-free electron lasers.
Oh, interesting. So they borrowed from a different area of research.
Yeah, exactly. And these X-ray lasers are already pretty amazing machines, like the LCLS, the LUNAC coherent light source at SLAC.
Right.
So instead of just relying on those microwave fields, they use lasers to shape the electron beam.
Okay, so instead of like a general push, they're using a laser for more precise control.
Precisely, lasers can interact with the electrons in a much more targeted and refined way.
I see. So it's like the difference between using a hammer and a scalpel.
That's a great analogy.
But I imagine actually implementing this with an electron beam, moving at almost the speed of light in a huge facility that can't be easy.
No, it's incredibly complex. We're talking about an accelerator that's a kilometer long.
A kilometer?
Wow. And that crucial interaction between the laser and the electron beam, it happens in just the first 10 meters.
So they have to get that initial shaping perfect right from the start.
Absolutely. Then that beam has to travel the rest of that kilometer without losing its structure, and then finally it gets compressed down to that submicron scale.
It's like a carefully choreographed dance of light and matter.
It really is. And the researchers spent months testing and refining this technique to make sure it worked perfectly.
Months. That's dedication.
Yeah. But it paid off because now they have this incredibly powerful and precisely controlled electron beam. And as you said earlier, it opens up a whole universe of possibilities.
Exactly. So let's dive into some of the areas where this could lead to major breakthroughs.
Okay, so one area is quantum physics.
Okay, the study of the really, really tiny.
Right. And this beam, because it's so precise, it could allow scientists to probe quantum phenomena with a level of detail that's never been possible before.
Like imagine seeing the interactions of individual particles.
Exactly. We could potentially test some of the most fundamental theories about the universe with much greater accuracy.
It's like having a new superpowered microscope for the quantum world.
And then there's materials, science.
Okay, so understanding the stuff that makes up everything around us.
Right, and this beam could help us study the structure and properties of materials at incredibly tiny scales and under extreme conditions.
Oh, so like simulating the intense pressures and heat deep inside a planet.
Exactly, which could lead to the discovery of brand new materials with crazy properties.
Like super strong or incredibly lightweight materials.
Exactly.
The possibilities are endless.
They really are. And then there's one application that I find particularly mind-blowing.
Tell me.
It's the idea of recreating star-like filaments right here on Earth in the lab.
Wait, what? How is that even possible?
So by focusing this powerful electron beam onto a target, either a solid or a gas, they can create conditions that mimic the formation of these energetic filaments that we see in stars.
So they're basically creating mini stars in the lab.
In a way, yeah. And as one of the lead researchers, Claudio Emba, put it, scientists know that these filaments occur, but now we can test how they occur and evolve in the lab with the level of power we haven't had before.
That's incredible. It's like bringing a piece of a star down to Earth.
And it allows them to study these complex astrophysical phenomena in a controlled environment.
Which is something that was pretty much impossible before.
Right.
It's amazing to think that this breakthrough could have implications for understanding the universe on such a grand scale.
Absolutely. And there are so many other exciting avenues, too, like the researchers at FACET-II, the facility where all this is happening. They're already using this new beam to advance plasma wakefield technology.
Oh, right. I've heard about that. It's a promising area for developing even more powerful and compact accelerators in the future, right?
Exactly. And looking even further ahead, there's the potential to compress these electron pulses even more.
To make them even shorter.
Yeah, down to the attosecond scale.
Wow, an attosecond is like unimaginably short.
It's 1/quintillionth of a second. So think about it this way. An attosecond is to a second what a second is to about 31.7 billion years.
That's mind-boggling.
It is.
Yeah.
And with these attosecond pulses, we could essentially take snapshots of matter at the atomic and even subatomic level with incredible time resolution.
So it's like having a camera that can capture the movements of individual electrons.
Exactly. And as Claudio Emma also said, if you have the beam as a fast camera, then you also have a light pulse that's very short. And now suddenly you have two complementary probes. That's a unique capability, and we can do a lot of things with that.
So we could watch chemical reactions unfold in real time, see how bonds form and break.
Exactly. It's like opening up a whole new window into the world of chemistry and physics.
It's clear that this isn't just about building a more powerful beam. It's about creating a tool that will transform our understanding of the universe at every level.
Absolutely. And what's really cool is that FACET-II is a user facility.
Oh, right. So it's not just for the team who developed this technique. Yeah.
Exactly. Scientists from all over the world can apply to use this technology for their own experiments.
That's amazing. It's like a giant playground for cutting-edge science.
And as Claudio Emma put it, if you need an extreme beam, we have the tool for you, and let's work together.
I love that collaborative spirit.
Me too.
And for anyone who wants to dig into the nitty-gritty details of this research, the team published their findings in Physical Review Letters on February 27, 2025.
Yeah, it's a fantastic paper.
And it was all made possible thanks to the support of the DOE Office of Science.
Absolutely.
So to wrap it all up, we've learned how researchers at SLAC achieved a major scientific milestone. They created a record-breaking, precisely controlled electron beam that's 5 times more intense than anything before.
Right.
And they did it using a clever new laser-based technique.
That's right.
This isn't just an incremental improvement, it's a game changer that opens up countless possibilities for scientific exploration across so many fields. We're talking about the potential to probe the fundamental workings of the universe and the nature of matter in ways that were unimaginable before.
Yeah, and I think for our listeners today, it's a great example of how even research that seems very specific can have ripple effects across the entire scientific landscape.
Right, like who would have thought that a new type of electron beam could lead to breakthroughs in everything from astrophysics to quantum physics?
Exactly. It's a great reminder that science is interconnected and full of surprises.
It really makes you wonder what other seemingly impossible challenges are about to be solved.
Yeah, and what incredible discoveries are just around the corner.
Well, if you enjoyed this deep dive into the world of accelerator physics, hit that like button and subscribe to stay tuned for more explorations into the fascinating world of science.
Absolutely.
We'd love to hear what scientific topics you're curious about, so drop your suggestions in the comments below.
Yeah, we love hearing from you guys.
And for those of you who want to learn more about the tools and facilities we discussed today, we might have some affiliate links in the show notes.
Check those out.
Thanks for joining us on this deep dive. We'll see you next time.
See you later.
Bye.